In this video, we're going to be defining circular motion and talk about the different ways that you can quantify and calculate the motion of something that's moving in a circle. So to start us off, let's remember back to Newton's first law. This is the law where a body remains at rest or in motion unless there's an unbalanced force. Basically, an object will keep doing whatever it's doing. It has a tendency to remain. So it's the law of inertia. Now, if we were to extend this to changing direction, here let's imagine that I'm running late for school and I place plate of Pop Tarts on the top of my car. And then I start moving out of my driveway and I make it kind of down my neighborhood road. And while I'm accelerating slowly, the Pop Tarts actually stay on top. And then I take a sharp right turn out of my driveway. Now, what's going to happen to those Pop Tarts? Well, you can imagine they're probably going to fall off the car. And they fall off the car because they continue to do whatever they were doing. If I was moving straight, the Pop Tarts are going to continue going straight as I turn out from under them. So the result is I see the Pop Tarts move off the left side of the car, but in reality, they're not actually moving left. They're just continuing straight. They'll keep moving forward in a straight line unless there's an outside force acting on them. That suggests that an outside force is required to cause something to move in a circle. Now, we talked about this before. We defined acceleration as speeding up or slowing down. Those are both ways of changing speed, and velocity is speed with direction. So that means there's a third way to change your velocity, and that's to change the direction in which you are moving. So changing direction is a form of acceleration, and it's a form of acceleration that we're going to deal with today as we're looking at circular motion. So some of this is something you can already figure out and piece your way through. If you have each blade on this wind farm animation being 30 meters long, we can estimate the speed in meters per second of the tip of one turbine blade. We can do this using equations that we already know. We know that velocity is just a distance divided by a time. So if we know the distance that the blade is moving and the time that it moves that distance, we can calculate its speed in meters per second. Well, the distance traveled by the tip of one blade, it makes an entire circle. So it's essentially the circumference of the circle, and the circumference of a circle is 2 pi r. We know r is the 30-meter long turbine blade. That's basically the distance to the center of the circle. So we're going to plug in 2 pi times 30 to find that the distance that the tip of the turbine blade moves in one rotation is 188.5 meters. Now I can time that duration. That time for one revolution is approximately 2.9 seconds if you were to take out a stopwatch and time that. And then I can figure out how many meters per second, just plug in 188.5 divided by 2.9 and I've got approximately 65 meters per second. So it's flying as it's moving around. It's going very, very quickly. And we did all of this without any circular motion equations, if you will. That's just the definition of what velocity is, meters per second. This is a form of velocity that we can talk about with circles. Call it the linear velocity. So at any given point, even if an object is moving in a circle, it has an instantaneous linear velocity. So basically, you're looking at such a small gap that the radius of curvature is kind of negligible, and that velocity is in the direction that's tangent to the curve. So imagine you're on a carousel here, a merry-go-round. Tangent to the curve is basically the direction that the horse is pointing at any given instant. Or here, if we look at the top view of this, at any moment, tangent to the curve, each one of these horses has an instantaneous linear velocity pointing in the direction that the horse is pointing. We can calculate that linear velocity. The official equation is the one that we kind of derived together there for the wind turbine. It's a distance divided by a time, where the distance is the complete revolution, this one circumference, 2 pi r, and the time is a special physics quantity called the period, the time for one revolution. Now, you'll notice that this is a generic way of talking about a circle. That if I were to go around one time and the circle had a radius of 1, I could calculate my circumference, the distance that I travel. It's 2 pi times r. In this case, r is 1 meter. So 2 pi times 1 meter is 6.28 meters. If I were to change my circle and grow it, it's really easy to change my circumference. I just swap out the radius, 5 instead of 1, and now my circumference is 31.4 meters. All right, so what can we do with this if we don't know anything about the circle? We just know it's a circle, and I've gone around once. We can think of this in a more generalized form. We call this a radian. So basically, instead of plugging a number in for a radius, let's just call it r. And imagine that we take that r and we want to go all the way around. It's 2 pi times r to go around. Well, that r is a new unit, basically. So instead of 1 or 5, we take that r and imagine you like stretch a piece of tape to measure the radius, and then you lay that tape along the outside of the circle. This amount of the circle that you have swept with one radius worth of circumference distance is 1 radian of the circle. If you kept doing this, obviously there's more than 1 radian in that circle. Turns out it's just a little bit over 6. It is 2 pi radians. So based on the definition of our circumference, it's 2 pi times that radius value, so 6.28 roughly radians worth to make it all the way around the circle. This allows us to talk about how much of a circle we've gone without needing to know how big the circle is. That's going to be useful for us. So let's see a couple examples. If a child on a merry-go-round rotates 3.5 times, what is their angular distance in radians? Well, 1 time is 2 pi, 2 times, 3 times, and then half a time. We can just basically say 3.5 times 2 pi, which is the time for once around, is 7 pi. In physics class, we don't like to leave the pi. We're going to expand that out to a decimal, and that's roughly 22 radians. Okay, so I can take 3.5 revolutions and turn it into radians. How many radians worth of a circle I've gone? Certainly more than 6.28. It's more than 1 revolution. All right, if an ant is on a record player, spins for an angular displacement, or probably better stated as an angular distance, of 14 radians, how many revolutions has it experienced? Well, that 14 radians is the total number that is larger than 6.28. So it's more than one circle. It's probably around 2 circles because it's about twice 6.28. I take 14 divided by 2 pi, the amount of radians for one circle, and I can figure out, well, it is a little bit over 2. It's 2.23 revolutions to make it 14 radians. Okay, so we can measure how far you've gone in a circle. Instead of revolutions, we can talk about it in terms of radians. Now, the other aspect of this that we had mentioned in that definition of linear velocity was the period, the time for it to go around once. So period is a special physics quantity that we'll see again when we get into circular motion. Well, circular motion and then again in waves. Period is represented as the time for one complete revolution. We'll describe it with a capital T in equations, and it's typically measured in units of seconds. So we'll convert it into seconds if it's not already. Capital T is the period for one revolution. Lowercase t is a more generic time that isn't necessarily fixed in as one time around. So here let's look at a comparison then to linear motion. Linear motion, we said, was v. That's distance divided by time, or d over t. Uh, Circular motion, we'll talk about this as an angular distance divided by time. This has a new symbol. We're going to call this angular velocity. It's actually a lowercase omega symbol. It looks like a little smooth W, but it's lowercase omega. It's a Greek letter. And that is measured in radians per second. Whereas my linear motion was a distance in meters divided by time, meters per second. Angular velocity is radians per second. Now that kind of brings up this idea of what's a radian. If you have a single revolution, a radian is your angular distance divided by time. You've gone around once, that's 2 pi radians. So the time for one revolution is t. We just say 2 pi over t. Now, this definition for angular velocity is not given in the data booklet. You don't get that equation explicitly. We'll see where it's kind of hidden in there as well. So we can use that idea. A Ferris wheel takes 40 seconds to make one full revolution. What is its angular velocity in radians per second? Well, omega, the angular velocity, is 2 pi divided by t. 2 pi radians for one revolution, and 40 seconds for that complete revolution. So basically we say 2 pi over 40 is 0.157 radians per second. This Ferris wheel per second doesn't make it very far around its circle. It is not measuring how much distance is traveled, but how much of the circle it's gone. 6.25 would be one complete time around. So it's definitely less than one complete time. A car tire rotates with an average angular velocity of 29 radians per second. In what time interval will the tire rotate 3.5 times? Well, a couple different ways we could solve this problem. We could take this idea of an angular distance in radians divided by time and figure out, well, It goes 29 radians per second, and the total number of radians is 3.5 times 2 pi. We saw that earlier when we were trying to figure out the radians for 3.5 times around. Same idea. And then we divide it by the time. Well, the only thing I'm missing here is time. I would find that the time is roughly zero point 0.5 or 0.758 seconds. If I did the same thing using my definition of like one time around, I could say omega is 2 pi over t. In this case, omega was 29 is equal to 2 pi over capital T. Notice the difference, capital versus lowercase. This is the time for going around once is 0.217, but I'm asked to find the time to go around 3.5 times. So I'll just multiply that by 3.5 and I'll get the same number. So there's a couple different ways you can solve these. Just think about it as radians per second. Figure out how much of the circle you're talking about and then time it appropriately. All right, now if we know that V is 2 pi r over t, and omega is essentially 2 pi over t, one circle worth of radians divided by the time for one time around, I see that in here. There's a 2 pi over t built into this equation. So instead, I could define V in terms of omega and my angular velocity, and just say V is equal to omega times r. It's the only thing that's different in there. This is how this omega definition is hidden in the data booklet. It's not actually in A2, but you'll see that it is the only difference between those two different versions of linear velocity. 2 pi over t times r is equal to omega times r. So you can kind of see where omega fits in there in that sense. All right, let's look at an example comparing these two ideas. If the carousel spins at one complete rotation every 10 seconds, that's what's animating now, what is the angular and linear velocity of each row? Well, each row here has a different radius, so that's probably going to play into this. If I'm trying to find omega, the angular velocity is 2 pi over t. The time is 1 or 10 seconds to go around once, so 2 pi over 10 is 0.63 radians per second. If I took that to solve for v, 0.63 times the radius, 2 is 1.3 meters per second. So two different ways that it can describe the velocity, how much A is moving. Well, if I look at B, the only difference is the radius. If I look at angular velocity, you'll notice that there is no radius in here. 2 pi over 10 still 0.63 radians per second. A and B, while they are at different radius values from the center, they are moving on the same circle, so they sweep the same amount of circle in 1 second, regardless of where they are. The total angle that they've made it is about the same. V is going to change. I take that 0.63 times 3, it's 1.9. So I'm actually traveling faster on the outside because I cover more ground. It's a bigger circumference in the same amount of time. So if you're looking for a thrilling ride on a carousel, get into the outermost lane and you'll be moving a little bit faster because you're a little bit farther away. So we can also answer this in some word problems. If you're sitting 4 meters from the center of a carousel spinning at 12 radians per second and throw a ball in the air, how fast would the ball continue in a straight line? So continue in a straight line, we're suggesting that we're going to be going now to a speed that's in meters per second. I know that the radius is 4, angular velocity is 12 radians per second, and I know this relationship. V is equal to omega times r. The only thing I don't know is V. 12 times 4 is 48 meters per second. A woman passes through a revolving door with a tangential speed, that's the same thing as a linear speed, of 1.8 meters per second. If she is 0.8 meters from the center of the door, what's the door's angular velocity? Again, I know V in this case because it's meters per second, and R is 0.8. V is equal to omega times R, and I can convert into omega, which is 2.25 radians per second. So it's about one time around for that angular velocity. Okay, so that's velocity. That's measuring how fast something is moving in a circle. The most important part when we get into circular motion going forward, though, is connecting to forces. And the way that we connect to force is through acceleration. And remember, there are three ways to experience acceleration: speeding up, slowing down, or changing direction. We are going to be focusing on the changing direction. We're going to quantify it. We're not going to derive this equation, but acceleration represents a rate of change of velocity and its direction. So even if the speed is staying the same, it is still accelerating, and our way of turning that into an acceleration is acceleration in a circle is its velocity squared, meters per second squared, divided by the radius, how far you are from the center of your rotation. And the direction of this acceleration has to do with how the velocity changes. So if you are on this carousel, say this was your initial velocity, and then a little bit later, this would be your final velocity once it rotates. The difference between those two, how that velocity changes, is basically another way of looking at your acceleration. So here, it changes in this direction, basically in halfway between those 2 points directly towards the center. So the important thing to get from this is the acceleration of an object in a circle will always point to the center. Now we are assuming a uniform circular motion, which means the speed isn't changing, but the direction is. That is always going to point us towards the center, no matter where you are on that circle. And we can calculate that in a couple other ways. If we're given this a is equal to v squared over r, well, I have a couple equations for v. If I plug in this omega r instead of v, I can expand that to be omega squared times r squared over r. One of my radius crosses off, and then I get a is equal to the angular velocity squared times r. I could do this using my other definition for linear velocity here, 2 pi r over t. I plug that in. That 2 gets, or the squared distributes to everything, and it turns into 4 pi squared r squared over t squared divided by r. Notice we're getting a pi squared. We don't see that very often. This t squared can go down to the bottom because I'm dividing with a fraction, and that turns into 4 pi squared r squared over t squared r. And then just like we did in the last slide, one of these r's can cancel out, and we get 4 pi squared r over t squared. Now, both of these equations for acceleration show up in the data booklet. We have actually 3 different forms of acceleration. You are going to use the one that matches the things that you know. So if you know meters per second, that's v, and you'll use v squared over r. If you know radians per second, that's omega, you'll use omega squared r. And if you know the timing of one time around, you'll use the last one that uses t. So if a carousel spins at one complete rotation every 10 seconds, what is the acceleration for each row? I could use either of these to factor in. I'm going to use this a is equal to v squared over r and plug in my v, which is 1.3 squared over 2. That gives me 0.843 meters per second squared. Notice we use the same units as linear acceleration. Here, to find at row B, it's 1.9 squared over 3, which is 1.2 meters per second squared. So the acceleration is a little bit higher on the outside than it is on the inside. All right, now I mentioned that acceleration is going to lead us towards a force. We haven't seen a force yet. We know from Newton's second law that every time there is an acceleration, there must be a force causing that acceleration. Things don't accelerate unless there's an unbalanced force changing it. And that's true when you're speeding up or slowing down. You got like a force of thrust or a force of friction braking. But it's also true if you're moving in a circle. So there must be a force causing that circle to happen. Think about the Pop Tart sliding off the car without a force keeping it on the car, it did not form that circle. So without a force, straight line, with a force, you can move in a circle. We have 3 different ways of calculating acceleration. But once I have acceleration, F is equal to ma. The force, net force, is the mass times the acceleration. I can plug that in, multiply by the mass to get a force. So let's do that. I've got a 3 kilogram rock swinging in a circle of radius 5 meters. If its constant speed is 1.6 radians per second, what is the acceleration in force? Well, let's list what we know. We know that the mass, m, is 3 kilograms. We know that r, the radius, is 5. And then my speed is in radians per second. Radians per second is an angular velocity. So we'll treat that as omega is 1.6 radians per second. Now, I know that I can use any of these 3 acceleration. I'm going to use the one that incorporates the things that I have. I know a radius and I know omega, which is the angular velocity. So angular velocity squared times r is 1.6 squared times 5, or 12.8 meters per second squared. If I know an acceleration, I can find a force. Force is just mass times acceleration. I know acceleration now. 3 times 12.8 is 38.4. So my way of getting to a force is first find the acceleration, multiply by the mass, and you'll have force. Let's do one more. A pilot is flying a small plane at 30.0 meters per second with a radius of 100 meters. If a force of 635 newtons is needed to maintain the pilot's circular motion, what is the pilot's mass? All right, here we're going to have to work the other direction. We know a force, um, and we're trying to find a mass, which means I must need the acceleration to do that. The things that I know, in this case, is meters per second, not radians per second. So that is v, a linear velocity, 30 meters per second. R is the radius, so 100, and F is the force. I need to know the mass. The only equation that's going to have mass for me is F equals ma, or in this case, F is equal to m times what acceleration is, v squared over r. You'll see a lot of times we'll just plug it in to begin with instead of calculating a separately. And I can plug that in. 435 is equal to the mass times whatever the acceleration is, 30 squared over 100. That will find a mass of 70.56 kilograms. All right, there's a lot in this video. You should be able to convert between angular displacement in revolutions and radians. So basically quantifying what a radian is. You should be able to define and measure what the period is of circular motion. Remember, just one time around, how many seconds that is. And then use that to calculate an angular velocity and be able to describe and calculate tangential velocity. So this linear speed based on angular velocity and radius, or just the circumference and your time. You should also be able to determine the direction and magnitude of centripetal acceleration and centripetal force. That's just a fancy term for the acceleration making a circle and the force making a circle. And be able to identify circular motion properties in a description and then choose the appropriate equation to relate them. So know if the speed that's given to you is an angular speed or a linear speed, and that informs which equations that you'll use to calculate acceleration and ultimately calculate the force.